you to keep in mind that it applies also to insects and disease and other things as well. Before I talk about invasives, I want to spend a little bit of time talking about climate change because it means many different things to many people. I'm going to try and define it in terms of what it means for plant biology. So to begin with, we have the observation that atmospheric CO2 is going up. Where does it come from? Well, it's not really difficult. If you take a source of carbon, whether that source of carbon is oil or coal or natural gas, and you oxidize it, that is to say you burn it, you take carbon, oxygen, put it together, you get carbon dioxide. About 90% of that comes from fossil fuels and cement. About 10% of it comes from land use change, primarily deforestation. Where does it go? Well, about half of it remains in the atmosphere. About 25% of it gets reabsorbed into the forest, and about 25% of it gets absorbed into the oceans, making the oceans more acidic. It's pretty straightforward chemistry. So if you look at the Keeling curve, which is the longest continuous record we have of monitoring CO2 from Mauna Loa, Hawaii, this is a little bit out of date right now. I think we're around 410 parts per million, 405, 410, somewhere in there. If you go back in time, for at least 1 million years or so, what you find is that the CO2 concentration has stayed between 200 and 300 parts per million. Current over 400 parts per million that we are observing is, at least in recent geological time, is unprecedented. How much more will it go up? Well, depends on the model. I won't go through all the different models, but we'll call the two sort of extremes here, this lower green line, we can refer to as the everyone drive a Prius and ride your bike to work, turn your thermostat down line. And then we have the red dashed line, which is the business as usual line. And right now we're pretty much along the business as usual line. There's been, even with the Paris Accords, no net change in terms of overall CO2 emissions per se. So we expect that to keep going up. How much more will it go up? Well, for the business as usual line, it's probably going to be somewhere on the order of 800 to 1,000 parts per million by the end of the current century, roughly, okay? So the next question is, so what? Yeah, who cares? Well, who cares if CO2 is 300 or 400 or 600 or 800? What the hell difference does it make? I'm going to offer two differences, two reasons why it's important. And the first is related to global warming or climate change. Now we know that there are various gases in the atmosphere. Nitrogen, oxygen, argon are the primary gases. But there are two very important gases which we refer to as global warming gases, carbon dioxide and water vapor. Now what does that mean, though? What do we mean when we say global warming? Well, the best example I can give to you is the guitar. How many of you have ever played a stringed instrument before? Any hands? Anybody know play a guitar ever in their lives? Really? Oh, okay, I'm back there. I didn't see the hands up front. So I'm going to ask this question of you. If I tune two strings of my guitar to the same frequency, let's say A, 440 hertz, right? Whatever. I tune those two strings to the same frequency and I hit one of the strings. What will the string next to it do? It'll vibrate. What if I'm a Methodist? Will it still vibrate? Yeah? What if I'm a libertarian? Are you telling me that the laws of physics and nature are actually consistent between political affiliation and religious denomination, and that might be a good way to make laws based on what the, oh my goodness, look at this. You crazy liberal. It turns out that that's true. But what does that have to do with these molecules? Well, it turns out that in addition to resonance in a guitar, these molecules resonate. They don't resonate in the key of A, they resonate in the key of heat. So whenever they encounter heat or infrared radiation, they absorb some of that. And it keeps that heat from leaving the Earth's surface. In fact, without these molecules, the average temperature on the Earth would be about minus 18 degrees Celsius. They are responsible for what is considered to be a natural greenhouse effect. But as with all effects, there's a Goldilocks factor, right? If there's not enough of these greenhouse gases, it's too cold. If there's too many of these greenhouse gases, it's too warm. So when you look at climate change or global warming, that's really what we're talking about. But there's one little wrinkle in here. You notice that I said CO2 and water vapor, right? So the changes in chemistry that we see are responsible in part for what's happening with respect to the change in temperature. It doesn't matter if the CO2 is coming from you or coming from a volcano. It does the same exact physical response. It's going to make surface temperatures warmer. But the wrinkle is related to water vapor and CO2. So if I looked at the Earth as a whole, where on the Earth is the air wet and warm? That is to say, where on the Earth is water vapor the primary greenhouse gas? I think somebody whispered tropics. Who whispered tropics? Raise your hand. Okay, you're right. That's exactly right. So in that case, in the tropical area, we don't expect to see the rise in CO2 to have as much of an effect. It'll be a little warmer, a little wetter. Now, reverse that. Where is the air dry, doesn't hold a lot of water vapor, and therefore adding CO2 will have a disproportionate effect in terms of surface temperatures. Sorry? North and south poles. So we expect to see that the temperature change is going to be precipitously faster at the poles because of its lack of water vapor. Is the air dry? In the deserts. So we expect the deserts to increase in size. So while one part of the country is likely to get warmer and wetter, one part is likely to get warmer and drier. Okay? Now there are other wrinkles to this as well. Go up in altitude, the air becomes dry, so we expect that higher elevations will warm faster. And one other last thing, if you looked at places like Maryland and Delaware, what part of the season has more humidity? The summer. So we expect to see less temperature change in the summer, but more temperature change in the winter. Now, I've taken an entire semester's worth of chemistry and physics and condensed it down into a 5-minute explanation. So bear with me. But having said all that, are there any questions about what I've given to you so far? Does it make sense?
How do you know what the CO2 was a million years ago?
Based on the air that's trapped in ice that is consistent with what we find at the bottom of long ice cores, you can actually tap into that air and determine what the CO2 concentration was at that time. But you can go back about 1 million years. Beyond that, we don't know. So at least for the last 1 million years or so, 200 to 300. Fairly well documented. Any other questions? Okay, now let's take that and do a second effect. Here are the before I get to that, plant biological consequences of temperature. Less temperature increases where water vapor is high, there's going to be more precipitation. Greater temperature increases with latitude or altitude, increasing desertification, increasing drought, rising sea levels from increased polar and glacial melt. Okay? Now, I want to give you a second effect, a second reason why you should care whether CO2 is 300 or 400 or 800 or whatever. Okay? This is a pretty basic elementary question. What do plants need to grow? And what are the resources that plants need in order to grow? They need sunlight, they need water, so they need light, they need water, they need nutrients, right? Nitrogen, phosphorus, potassium, etc. What else? Carbon dioxide. 95% of all plant species lack the optimal amounts of CO2 in order to grow. Now, suppose for the sake of your imagination that one of these resources was to go up by 30%. Let's say, for the sake of argument, that, I don't know, the amount of phosphorus had gone up by 30% in your lifetime. Would that have an impact on what you grew? Not a trick question, I promise. Of course it would, right? Would every species of plant respond the same way to that 30% increase in phosphorus? No. If you were a plant breeder, would you want to breed as a means to optimize that phosphorus? Of course you would. So, in fact, CO2 has gone up by 30% in my lifetime, directly measured. How many of you right now are breeding or selecting for CO2 responsiveness among whatever it is you're growing? Anybody on Google right now? I know I'm pretty boring. If you could go on Google. Anybody have access to Google? Would you do me a favor? Who has Google? Okay, do me a favor, would you? Would you type in on Google marijuana and CO2? Marijuana and CO2. And just type and just read out the first link, the first hit you get. Say it loud so everybody can hear you.
Scholarly articles.
The first one.
How to use CO2 to increase cannabis yields.
Can you say that really loud?
How to use CO2 to increase cannabis yields.
How to use CO2 to increase cannabis yields. If the marijuana growers can do it, why can't the soybean growers? Why can't the wheat growers? Why can't the oat growers? I'm talking about, we'd say challenges, but there are also opportunities here. So here's one of the examples. This is from the ExxonMobil website, and this is loblolly pine, showing growing with more CO2. And you can see, woo, loblolly pine grows more. Isn't that wonderful? That's great. Except missing on the ExxonMobil website is this particular species, poison ivy, which also responds to CO2. So you see the difficulty. When I change a resource, when I change temperature, not everything that you want to grow is going to respond the same way. And that's important in the context of invasive species. So when we looked at a large FACE, or free air CO2 enrichment experiment, which was done at Duke University, this is an amazing, God, I think they spend $1 million a year on CO2 alone, looking at how CO2 would cause the loblolly pine to grow more. The loblolly pine, remember, is what I showed you in the ExxonMobil website photo. But in fact, we found that it was the poison ivy that responded more to rising CO2 than the loblolly pine did. And that's a lesson to be learned in the context of looking at weeds and invasives. You don't anticipate what will respond to that sudden shift in the environment, but we think weeds are primed to adapt to it. Again, CO2 is a fundamental resource for plants to grow. Not all plants are going to be beneficial to human society. Who knew, right? And not all plants will respond the same way, and CO2 will also alter qualitative components of plant biology. Any questions to that so far? Make sense? Okay, I see a few nods. I see a few people whose eyes are closing, so more coffee, right? Okay. So invasive plants, there's a cost. There's an economic cost in the billions for the US, and there's also an environmental cost because they reduce diversity. And so I'm going to talk a little bit about one of my favorite invasive species. I love Kudzu. I know I'm one of a handful of people, but you know, I think it's like the greatest thing ever when it comes to studying invasives. So I want to give that as an example because we've been studying it for the last 18 years. Now, back in the early 1970s, for the Midwestern part of the United States, this was the northern limit of Kudzu, right? We wanted to focus on the middle part of America, in part because no mountain ranges, there's no major metropolitan areas, and whatever migrated could migrate up and down. So we wanted to see whether or not the winters, which I suggested to you earlier, are warming faster than the summers, could in fact be contributing to a northward migration of kudzu. So a pretty basic question, except we needed to kind of define some terms. And one of the first ones was done by Heather Coyner, who is was at the University of Toronto. And what she did is she looked at a number of different kudzu populations, because kudzu has been introduced into the US in a number of different ways. And she said, okay, what's the absolute lowest minimum temperature that kudzu can survive? And basically, she used a relative conductivity, which is you apply electricity over the stems, and if the cells rupture, then the electricity will be conduced. If they don't, then the overall resistance is high. And to make a long story short, she found that even a one-day exposure of minus 28 degrees Celsius ain't going to go past that. So we use that as sort of our thermal limit. And then we looked at, has this minimum temperature threshold changed? Now, as a scientist, I have to show you at least one slide with a lot of data on it that nobody in the back row can read. So this is my contribution to that. So let me try and just briefly, this dashed line here that you see is that minus 28 degree line, okay? These are the different locations. This is the minimum yearly temperature, the lowest recorded temperature that we could find for that site, beginning back in the early 1970s and then moving forward to about the mid-2000s. What you see, this is a 95% confident interval, is that for every location that we sampled, okay. So if we now go to 2006, this is the northern limit for kudzu in the midwestern part of the United States. Doesn't mean this is solid kudzu happening here, but this is now where kudzu is being found. Well, let's push our luck. Let's look at 45 degree north, halfway between the equator and the pole, this line right here. How fast is this line warming? Well, we looked at these sites, Minnesota, Wisconsin, Michigan, Ontario, and you can see the warming winters occurring, but again, they're still below this minus 28 degree line. But when will it be above it? When will it get warm enough in any of these locations for kudzu to grow? So these are the dates that we projected where kudzu will show up along this 45 degree north line. 2022, 2019, 2015, and 2015? Whoa, hey, it's 2018. Did kudzu show up? Yes, it did. Based on the EDD maps right here in this Bodie County, Michigan, along the 45 degree line in 2011, kudzu showed up. This is, if you haven't accessed this, by the way, early detection distribution maps, eddmaps.com, gives us a county by county breakdown of where kudzu is now showing up. So if you want to see if kudzu is in your county, you can easily go to it and keep track not only of kudzu, but many invasive species. So Benzie County is where it showed up. So the other reason we're interested in kudzu is that it also is a host for Asian soybean rust. Kudzu and soybean are related, and while the rust itself is actually more sensitive to colder temperatures, there is a possibility that it may also spread as these winter temperatures become warmer. So in terms of looking at the monitor part of this with respect to kudzu, as winter temperatures warm, kudzu appears to be expanding. Not too surprising. What else is going on? Well, it's likely that other pests, other weeds, other insects, other diseases are going to be spreading as well as winters warm, because winters are a major limitation in terms of, from a human health perspective, the CDC is monitoring, and the spread of disease that moves northeastward, we need as agriculturalists to do the same efforts in terms of monitoring where these new pests are coming from. Unfortunately, there is no systematic monitoring currently in place to measure climate change and the movement of these invasive pests. Now, let's segue to a wrinkle that's a little closer to home here in Maryland. Well, I noticed that in this Keeling curve, they did it in Hawaii. What the hell? Why would you go to Hawaii to monitor CO2? Right? Well, daiquiris, I don't know. Timeshares, maybe there's some really good reason why you want to go to Hawaii. Why do they go to Hawaii to monitor CO2? That seems really weird. Oh, because you can monitor it at 10,000 feet in the most geographically isolated spot on Earth, where the only thing you're going to see is the background CO2. Trust me when I tell you that the CO2 in this room, with all of you breathing heavily, is not 405 parts per million, right? So that's the background. That's why we monitor it there. But there's something different about that. What if we wanted to look at invasives in real time? Projected, but in real time, what's happening now? Well, I know that Baltimore, the CO2 and the temperature are not the same as the surrounding. Maybe we can use Baltimore as a harbinger of things to come. So that's what we did. We went from an organic farm in western Mass to a common location at USDA, which had a seed bank of about 40 different species, including some invasives. We dug our plots, we moved the soil, we made the soil as uniform as possible, and we monitored the hell out of it. And we kept the soil watered the same along the site. So when we did that, we found that when you go from a rural to a suburban to an urban location, the CO2 went up by about 20%. The daytime temperatures went up, the nighttime temperatures went up. The growing season was longer. And well, what about other things? Well, ozone was a consideration, but in fact, when we saw ozone events occurring, they also occurred within a few hours at the organic site. So overall, the urban areas are a pretty good surrogate of what we can anticipate in the near term with climate change. So what happens? Well, we're getting ready to harvest our first crop, such as it is, and whenever you have a bare field, as you know, first thing that comes up in a bare field when all else has been removed are weeds. So I am very proud to say that we got good weeds. We got lamb's quarters and ragweed. And boy, I was very proud because according to all my textbooks, lamb's quarters gets to be about 6 to 8 feet in height. And we had 6 to 8 foot tall lamb's quarters. Woohoo, right? Pretty damn good. You have to be a weed scientist to really appreciate that. So except that when we went downtown, I got 10-foot tall lamb's quarters. I set the dubious record for lamb's quarters in Maryland, right? Why was it growing so much bigger in the urban area? Well, because we had more CO2, we had warmer temperatures, we had a longer growing season. So all of those things are affecting nasty weed in real time. Now we go forward after 5 years. As you change, well, of course, things go through a progression. You get weeds, and then you get shrubs, and then you get trees, right? Takes about 50 years, unless you're doing it this way. After 5 years, we have our neutral shade cloth up, and we're getting ready to harvest again, and that's our site. Whoa! How the hell did that happen? Atlantis, tree of heaven, is part of our seed bank, but we never expected it to grow that quickly over 4 years. So what we think is going on is that when you looked at the overall litter between the locations, it was in fact the urban location, because it had so much more biomass, that basically when it died and went back to the ground, it formed this really nice mulch. Well, what happens when you mulch? Well, you basically try and defer the germination of the small seeds, but the bigger seeds, the trees, the shrubs, came through. And so we had this very sudden shift in terms of the demography of what was going on at these sites. And what's interesting about that is that when you looked at the total biomass coming from the urban locations versus the rural, much of that biomass was in fact invasive. Species that had been included in with our original seed bank. So when you talk about climate change as something that's going to happen and my grandkids are going to worry about it, maybe urban areas are sort of a bellwether of things to come. And in fact, what may be happening in urban areas is that they are basically a place for invasives to reside because the conditions are good for their growth and their production of seeds. And again, I want to emphasize that this is not just with weeds. This is pine bark beetle. About 3 years ago, it crossed the border, across the Canadian border, or I should say, and more importantly, the Canadian Rockies here. So now it's moving eastward and only has to come down to the eastern part of the US. Southern pine beetle is moving up from the south. So that gives you some sense of the climate invasive paradigm as best we have at the moment. But what does it mean for pest management? Really have to worry about this. I mean, come on. I can go buy some Roundup. Really, you know, why is this a big deal? I'll buy some Roundup at Home Depot. I mean, we use quite a bit of it, actually. This is USGS data looking at glyphosate. I think we use about 180 million pounds per year. And you can see where we grow crops in the U.S., can't you? Pretty much right along this part of the Midwest basket, as it were. I mean, well, hang on a second. If CO2 and temperature are going to impact how weeds grow, would that impact how they respond to glyphosate? Let's find out. Okay, this is Canada thistle. This is a common weed, particularly if you go to no-till soy. This is ambient CO2, and we sprayed it with the recommended dosage. Yeah, got about 80-85% control, not too bad, not too bad. We sprayed it under 650 parts per million CO2, and we got 0 control. Why? What's going on? Well, it turns out that when you give Canada thistle more CO2, a lot of that extra carbon goes not above ground, but into the roots for storage. So here's the ratio of elevated CO2 to ambient CO2 over a 3-year period for shoots and roots. And you can see that a lot of that additional carbon was going below ground. Well, what difference does that make? Well, in the case of Canada thistle, it makes a big difference. Why? Because Canada thistle has one hell of a root system. And if you know anything about Canada thistle, you know that each little bit of root can, in fact, produce a new shoot. So what we think was happening is that we were spraying with the recommended dosage, but in fact, because CO2 was causing this additional root mass to occur, it simply was a dilution effect, that we didn't kill all of the root and the root came back. Now, can you overcome that? Sure, you can overcome it. Spray more glyphosate, increase the concentration. What does that mean for you? It means more money. Costs more. Costs more in terms of environment, costs more in terms of money. So here's my suggestion. For what it's worth, I'm going to try and do what I call the 3 M's. The first M is monitor. Things are changing faster than they have in the past, and it's important to keep track of what, in fact, is changing. Now, I'm going to go out on a limb here. This is going to sound a little science fiction-y to some of you. I don't mean it to be. So we need to keep track of weapons of incoming destruction. We spent literally $1 trillion keeping track of, during the Cold War, because the vessels might do enormous amounts of damage, like pine bark beetles, which can destroy 35 million acres in the US. Are we tracking pine bark beetles? we are in the US. Is Canada tracking them? They are. No. We have no global system. And that's a shame because, you know, the science fiction thing would be if there was just some sort of, I don't know, some kind of a handheld computer device, something that you could hold in your hand that, I don't know, what could you do? You could take pictures with it. And you could take pictures of invasive and pests and things and giant hogweed. You could put this handheld computer. I know it's crazy. And you could share this information with others. Hell, you could even get some kind of global system set up that could be run by some sort of large corporation that could advertise its products on your website so that you as a farmer could look it up and say, hey, what's the price of this thing coming into my area? I know, it's crazy. You know, a handheld computer, that's never going to happen in my lifetime. Is anybody doing that? Some people are doing it locally, but there is no global system for monitoring global pests, and that's a shame. It really is. Mitigate. We all understand the concept of early detection, rapid response. Does anybody recognize that plant? That's Kudzu. Really, honest, that's Kudzu. It's much easier to take care of Kudzu when it's like that than when it's like that. That's the reason why we have early detection, rapid response. And that's true not just for Kudzu, but true for most invasives. Manage. I know, at this point, it's easy to go out and spray. I understand that. And you can't weed by hand. But there are many opportunities within the IPM system, which back in my day, once glyphosate was introduced, everybody said, oh, we don't need IPM anymore. I talked to a medical doctor. He said, yeah, back in the day when we had antibiotics like penicillin, we didn't care about anything else. We just gave penicillin to everybody until there was resistance to penicillin, and then we had to go back and look at the ecology again. And that's kind of where we are right now. Most herbicide companies are. It's physical, biological, cultural, pesticides. What tools are available? When should you use them? Integration of IPM, especially in regard to emerging and climate-driven threats. So monitor, mitigate, manage are all very important. Some thoughts then. All three of these, forewarned is forearmed, proactive is better than reactive. And again, any tools in the toolbox. And I did a paper with Laura McConnell, who's now at Bayer Corporation, that's published in the Journal of Ag and Food Chemistry, if you'd like to see more of this in terms of some of the specifics of what we propose. And then I want to say one other thing. In addition, when all else fails, you turn crisis into opportunity. This is a YouTube video, but I can't get it to work. But basically, that's Asian carp. Asian carp is a major invasive of the Midwest. And it also has been referred to now as Kentucky tuna. And it is showing up in many of the local restaurants, where it is a nice edible fish. And the case of snakehead, it's also edible. And you can go now and find out on YouTube how to catch, clean, and cook snakeheads. There are very high-end fancy chefs in Baltimore who are serving snakeheads with endive and all sorts of things. But I don't have a good name for it yet. Maybe Chesapeake Chad, Baltimore bass. I don't know. You guys think of one that we could think of that would be applicable to how we can convert snakehead, because snakehead doesn't sound like something you really want to eat, right? So we need to come up with a better phrase for it. But again, if that's invasive, maybe one of the ways you make it less invasive is to turn it into an opportunity. So now what? How am I doing on time?
You're doing fine. We've got 10 minutes.
Good. Okay, I'll wrap up then. Invasive plant biology, well, any invasive biology in the context of climate change is important. You're likely to see new things that you have not seen before, and it's important to keep track of those. Right now, we have scattered efforts. As I mentioned earlier, the eddmaps.org website is a good site to go to if you're concerned about invasives in your own county, in your own neck of the woods. Unfortunately for us, as a government agency doing research, our overall budget has dropped by about 25% in the last 10 years. It's a challenge. They expect you to do with less until you do everything with nothing. So that's kind of where we are at the moment. We need to move beyond our silos. We need to sort of integrate among the different disciplines. I'm sorry, I said silos. The current administrative term is cylinders of excellence. So if we try and get beyond that, try and work together. And I think there are opportunities here. I think that we come from different backgrounds. We have different ideas. We have different ways of approaching problems. So we try and look for commonality. We try and look for things that we can come together on in terms of applying those resources to these problems.